I'm not sure if she's introduced yet, but I'll say a few words about her. Zoya Dimitrova. She's fantastic. She has a master's degree in computer science and also mathematical modeling. And she currently works for the CDC as a bioinformaticist. But related to Math Kangaroo, she was the one who founded the Georgia's first Math Kangaroo Center, and she's currently the director for the state of Georgia for Math Kangaroo. She's been involved in math coaching for over a decade, and ever since around 2009, she's been running math clubs. She also happens to be the one who's running the the levels 1 and 2 uh, classes for Math Kangaroo, and she was also the one who developed the curriculum. With that, I'd like to turn it over and let Zoya say a few words representing Math Kangaroo.
Thank you, Professor Lau. Dear students, I'm very happy to meet you all here, and thank you for the introduction, Professor Lau. I would like to invite you to participate in our competition called Math Kangaroo. I love this competition, and I'll tell you two main reasons that I love the competition. First of all, the problems. The problems are challenging, but fun. They rely on logic, not on rote memorization, not on a lot of computation. You have 30 problems to solve for 75 minutes, 10 problems for 3 points, 10 problems for 4 points, 10 problems for 5 points. The competition is always on the third Thursday in March for 75 minutes. So you dedicate 1 hour and 15 minutes to solve 30 problems. Why is this important? Not only that the problems are wonderful, but also this is a truly international competition. And there are not that many opportunities to participate in something together with more than 6 million students all over the world and challenge yourself with the same problems that the other students are solving. As the name suggests, the competition originated in Australia, then became very popular in France, spread in Europe, came to US 30 years ago, and now we had already more than 300,000 participants for the last 30 years, and last year 44,000 in more than 800 centers. So please check and try to register at mathkangaroo.org. And if there is no center, online or in person, that is close to you, why don't you start a center at your school or with your math club? It's easy. It's a great experience. We have extended our registration until February 1st, so we have plenty of time to register a center, spread the word. You need 10 other interested students to start a center, and you have the center, probably with the help of a math teacher or a parent. As I said, I love the problem and the opportunity to be in the environment that you are comfortable with your math club probably, but be part of a truly international competition. And the problems are selected every year with suggestions coming from all different countries. So we have more than 60 countries that participate now. So I hope you would check the competition and be part of it. And just a word, one of the leaders of this session today, Anshul Goku, is actually a participant in Math Kangaroo, and he can attest for this. And I was happy to meet him through the competition and give him awards about his participation and success. So thank you very much for the opportunity to invite you to participate in Math Kangaroo 2025.
Wonderful. Well, thank you very much, Zoya, and thanks very much for joining our session. With that, as you can tell, I won't really be able to discuss problems from here, but fortunately, we have two extraordinary people who are part of our live program, Eli and Anshul. With that, I'm going to toss it over to Eli and Anshul to lead the rest of this.
All right. Hello, everyone. Thank you so much for the introduction, Professor Lowe. We're going to introduce each other a bit more right now, but before we do that, I think we should actually look at a quick icebreaker to get you people talking. Ooh, I think I wanted to... Oh. We're gonna go for this one. Yeah, is cereal soup. Sorry, a lot of icebreakers, but here we go. Let's get us both spotlighted here so that we can discuss well. We're going to talk about whether or not cereal is soup. And Stephanie is already saying no, but
No.
Anshul, what do you think?
I mean, I would definitely have to agree that cereal would be a soup note because it just fits all the requirements.
Hmm. Yeah, I think Jian Ni agrees with you as well. He's also saying yes. Hmm. I mean, I could see it, Cereal is kind of just like the milk is like the solvent, I guess, the stuff that all the stuff is in. And then the cereal itself is just like the stuff floating on top, because most soups just have some liquid type thing and other stuff that's on top floating around. So I think it's pretty reasonable to say that cereal, at least when in milk, could be considered soup. Seems Carmel is saying it's cold morning soup. Yeah, I think that's a good description of it.
Yeah. I mean, I don't know. It's definitely a weird question, I'm not gonna lie. It's not your typical sort of question, but by cereal, I think cereal by itself is no milk. Yeah, that's like the most valued way to eat cereal, I can't lie.
Really? I don't know. I mean, I think it just like kind of dries out your mouth if you don't have any milk. Just eating dry cereal? I don't know. I just feel like it wouldn't really work. I think you need the milk for it to be even called cereal. I think without the milk, it just can't even be considered cereal at all.
You gotta eat it like chips almost.
I don't know.
Okay,
Then I
normal.
guess you could always put milk on the chips, and then I think that would become cereal. I think
Alright.
the definition of cereal really implies the milk, and then the other like crunchy stuff that's inside of the milk. And so in that case, I think it should always be considered soup. But I'm curious, are there any arguments you think against it being soup?
I mean, not really. I can't think of any.
That's fair. Yeah, I guess we're in agreement. Usually actually when I ask this question, people are pretty adamant that it's not soup. And I think I can understand why, because most soups, are like a savory type flavor, and the solvent is water, it's not milk. So I think it's like a very weird soup if it is a soup. But oh, Stephanie is saying milk is definitely not soup. I don't think Stephanie thinks the milk can replace the water as the fundamental, ingredient there. But okay, I I guess except for Stephanie, we're actually thinking that cereal is soup, but maybe all this discussion of cereal and soup has made you hungry, and so maybe we can satiate your appetite with some math. So let's get into some of these questions. How about we look at the first one? Okay. This is question number 1, and we're going to be just looking at the odd numbered questions. So we're going to be doing like 1, 3, 5, and so on. And this question asks, which of the following strings cannot be transformed into this string? So we have a bunch of strings, and we want to know whether or not they're equivalent to this. Kind of interesting. It's like a knot theory type question, although I've never really studied any knot theory. Anshul, what do you think about this one?
Maybe you can just go through one by one and see if they're possible. No, I think that would be pretty straightforward way. So, all right, maybe let's just look at option number A first, right? If we look at this shape, we can see that essentially what we first can do is like flip over this, where we have this overlap. We can just flip it to the other side, and then we're gonna get some straight thing like looks like this. And then we just flip it over one more time, and then we're given a straight loop, which is the same as this one, essentially, doing that exact same flip. So obviously, we want to look at ones that cannot be formed, right? So this one can be formed, so it's not this first option. So Eli, what do you think? Do you think B could be done?
I don't know. B looks a lot more knotty than all these other ones, right? I mean, for one thing, I just wanted to say in knot theory, I think this is called the unknot because it's not a knot, it's just a loop. And so indeed, I think this, if you just, flip it around, would just be a circle, which would not be a knot, so that's an unknot. And the same with A, because you could flip it around and then take out the loop there as well. But with B, it seems a lot more difficult because if I try like tugging on this side, then I'm going to get caught over here. It's going to get like hit against this loop over here. And so it looks like I can't just take it apart. Same if I try to pull over here. If I pull over here, it's going to get caught over here. It's really hard to draw this type of thing, but hopefully you can visualize it. So I'm starting to think that B is not an unknot. I think it actually is a knot. I think it's not possible to transform it into a loop. So tentatively, I think we can say that B is a possible answer, but maybe we should look at the rest of them just to make sure. So how about C, Anshul?
I think we get a really sort of similar situation to problem A, right? We have this sort of segment going over that, so we can like, sort of fold that upward. And once we fold that upward almost, we're going to get a shape that almost looks like, it's kind of hard to draw, but it actually is going to look like this, which is pretty much the exact same knot from before. Well, well, essentially the same sort of string. And then if those two are the exact same, then we're done. So this one can definitely be formed from the previous knot, so we're all good.
Yeah, and then if we look at D and E, I think we can see that they're also unknots because we can just flip this around, and then it's very obviously a loop. And then for E, you can just untwist and untwist, and so that's a loop as well. But it looks like B does not have these other properties. It can't just be made into this loop, so it looks like B is our answer. And I saw someone say in chat that it's a trefoil knot. I believe that is what this is. Honestly, I'm not totally sure what all the names of the knots are, but it has 3 things, so trefoil sounds like a good enough name. Let's see, are we correct here? We are, yay. Okay. Next question. Would you like to read this one for us?
All right. So first diagram, we have a rhombus, and then we add these 2 right triangles, and essentially now we want to figure out how much percentage did our area increase by. So yeah, I think we can just go about this note. We can just split this up, and originally we had 4 of these identical right triangles, and then now we have 6. And if we just simply look at the amount of right triangles this changes by, 4 to 6, that's just a 2 change or a 50% change, essentially, because 2 is 50. 2 is 50% of 4. So pretty straightforward problem, but it's definitely an interesting one though.
Yeah, I think this is kind of cool because we don't actually know what rhombus this is. This could be any rhombus. We don't know the side length or anything, but kind of a key feature of rhombuses is that their diagonals are perpendicular. And so this is indeed a right angle over here. And since this is a right angle, we have 2 right triangles that have to be congruent to these right triangles over here because this actually forms a square. And so, yeah, pretty cool. We're just adding 2 more triangles of the 6, or of the 4, so that's 50%. Increase. And let's see, are we correct with E? We are! Amazing. Okay, we're blasting through these. Maybe we can, hopefully some of these will take some more time. But now we have Julia cutting off the 4 vertices of a regular tetrahedron, and we want to know how many vertices the shape that remains has. Okay. So originally we had 4 vertices, right? It's a tetrahedron, there's 4 things, but for each of them, we've cut off a little end thing here. And it looks like we get 3 vertices where that 1 used to be. So if we're just getting 3 at each of these corners, I think that would just be 3 times 4, which is 12. Am I missing anything here?
No, I think you're all good. I think that's exactly right.
Okay.
All right, 12.
Let's see, are we correct?
Oh.
We are. Awesome. Okay. Guess we'll just keep going then.
All right, so we have a fruit bowl that contains 5 types of fruits: an apple, grapes, cherry, strawberry, and banana. And we're essentially given what other people like. I think we're supposed to match them up. We have Al likes apple, so we can pretty much pair that off already. He's gonna get that one. And then we're given Bach likes pretty much everything but grapes. Cam likes everything but apples. And Dom likes apples, grapes, and cherries. Eva likes apple and cherries. And the initial thing is, all we need to find out is who has cherries, but we already know that Adam has the apple. So if the apple's taken out here, all we're left with is the cherry for Eva. So Eva must have the cherry or else it just won't work out. So that's just a really nice adding. It simplifies the problem so greatly. We don't actually have to solve for anyone else. All we have to do is solve for Eva. And she likes the cherries. So that should be pretty much it.
All right, so it looks like we didn't even need any of this other information and that we just have Eva likes cherries. And is this correct? It is, Eva. Okay, and now I did just realize that we forgot to introduce each other. So,
Oh.
you wanna go do that now? Sure. You'll have no idea who was talking to you before, but now you'll know. It's because the person on my left is a 4-time Amy qualifier, a USA Physics Olympiad qualifier, and he also enjoys playing basketball and chess. So everyone say hi to Anshul, who, I mean, I guess you had no idea who he was before, but now you know.
All right, and then on my side is Eli. He's a 3-time AIME qualifier, also a perfect score in the USA Mathematics Talent Search. And then he also is a percussionist, which is super cool. I always love people in band. But yeah, that's just Eli.
Thank you for that introduction. Okay, so without further ado, I guess we can continue on. And if you are confused, as I see some people saying in chat, then you can send any questions you have into the chat, and we can go over anything that you want to go over again. Okay. But otherwise, we'll go on to the next question. Question 9. We have 4 different positive integers into these boxes, okay, and then covered up. Cool. The products of the integers in each row and each column are shown in the diagram. Okay, so the product of these two is 6, this two is 8, this two is 4, these two 12. We want to know the sum of the 4 integers. So probably we just need to find all 4 integers. Okay. Well, to get a product of 6, there's actually not that many ways I can do that. I mean, I can have something like 1 and 6, or I can have 2 and 3, and then the reverse of those. So, I mean, we can really just, like, put them in and then see what works. So, yeah, I think, well, for one thing, this is a 4 here. And so we can't have 6 or 3 here because then, 3 times something could never be 4. So it has to either be a 2 or a 1. Let's just try a 2, see what happens. Then this would have to be a 3. And this is fine so far because 12 is divisible by 3. So then this would have to be a 4, right? Because this would be, 12 over 3. If this is a 4, then this has to be a 2, and, well, it just looks like it works. Is there anything wrong here? No, I don't think so. Well, I'm actually curious, would it have worked with 1 and 6? If it was 1 and 6, then this could be 4 and 2, and I think that would work too. Yeah, okay, so I guess both actually work. Do they have the same sum? This would be 4 and 4 is 8, plus 3 is 11. No, over there it's 13. I'm confused. So, well, 11 is not one of the options. So I guess they weren't going for this one.
It's kind of interesting.
Is this an invalid solution? Oh, it says different. Oh, there it is.
Oh, there.
Different solutions. Different positive integers. So we can't have 2 2s. Okay, there we go. This one doesn't satisfy the different condition. Okay, so the one on Anshul's screen is the correct one. Looks like we have 13. All right, are we correct?
Nice.
Nice. Awesome. Okay, next question. Question 11.
All right, really interesting problem. So we have Carolina bakes a cake and cuts into 10 equal pieces, and we're pretty much taking a piece out and then spreading the other ones evenly. So, and now we even find like the angle measurement in this like little tiny like corner pretty much. So I think how would we approach this? I think we just solve for how many degrees one slice would be, and then simply splitting it up between these 9 different segments left. So if we have a whole circle, that's going to give us 360, right? And then beyond that, we're just going to divide that into 10 pieces, right? 360 divided by 10, that's just 36. And now that we have 36, we know that each slice is 36 degrees, and we're splitting that between these 9 gaps here. So all we have to do is just divide that, 36 divided by 9, and we're just going to get 4 degrees for each one of these spaces because we're splitting it up. And hopefully, there should be nothing wrong with my answers. And Caramel also gets 4. Always good when other people have the same answer as you. Oh, and the answer is 4. So, nice problem, nice problem.
Nice. Okay. We're going right through these. Question 13. Ooh, this looks interesting. A square has side length 10. It's divided into parts by 3 straight line segments. Okay, so this one is just a diagonal, but these 2 line segments, it's kind of weird. They're just like to this random point. We don't actually know this point. So that's interesting. I wonder if that'll affect anything. The areas of the two shaded triangles are A and B. What's the value of the difference of their areas? Well, automatically, just right off the bat, without even thinking about this question, since we don't know where this point is, that makes me think that for some reason these actually have like the same area, so it would be 0. Because otherwise, like, how would we know the exact value without knowing where this point was? So that just makes me think that the answer is going to be 0, but maybe we can figure out why that is. So, Anshul, do you have any ideas here?
I mean, not really. I think we can just fix the point wherever we choose, no, and then we'll just see what the areas would be. Because it doesn't really define it, right? So it's our choice.
We could do that, yes. And I think you see if you put it in this corner, then
Yeah, it would just be
indeed
the
you would
same
just get
thing.
2 diagonals, and they would be the same. But why are these always the same? I think I know.
Well, we can just look at these two triangles, no? Oh, this triangle and this triangle. And we can sort of look at the different areas of the triangles also and the regions that they share, right?
Yeah, I think that's kind of interesting because, well, this has a height that's, over here and has a base of 10. But this also has a base of 10, and it has the same height because it's within the same parallel lines. So it looks like these should have the same area, these two big triangles here. But if those have the same area, then what is the area of A? It's just that big triangle minus this little triangle. And B is this big triangle minus the same triangle. And since these are the same, that means that A and B must have the same area as well, because you're subtracting off the same area triangle, right? So I think that does show that A is the same as B. And so the answer should be 0. I think that's kind of awesome that we can just choose any point and we still get an area that is the same. Okay, 0 meters squared. Looks like we were right.
All right. So now we have John, always switching up the names. We have a large number of identical cubes, and we're making a structure by having this initial cube and adding another cube to each one of these faces. And then now he wants to repeat that step and make a bigger structure where he adds a cube to each one of these remaining faces on this diagram. So now we need to find out how many extra cubes do we need, right? So I think we can just pretty much go about just counting this straight up, right? If we think about like a sort of like a layering system, at this very top side, we're just gonna get 1, right? We're adding 1 to the cube to the very top. And then if we think about around that top cube, we're gonna get 1, 2, 3, 4, right? That's right. And we can just keep going on like that. And then on our middle layer, that's when our largest value would be 1, 2, 3, 4, 5, 6, 7, 8. Right, and then the very bottom, we have a repeat of the top, right? We're gonna have 4 again and then 1. So we have 1, 4, 8, 4, 1. That's the amount of cubes we're adding up, right? Now all we have to do is add these up, right? We want to find out the number of extra cubes that we need. So we add 1, so we have 1 plus 4, that's 5. 5 plus 8, that's 13. 13 plus 4 plus 1, it's just gonna give us 18. Oh, Carmelo also gets the same answer. Yeah, really nice, really nice. Should get options. Oh, option A, 18. And we'll see. Oh, that is correct. Really, really interesting visualization problem.
Yes, it is. And it's kind of tricky because you do have to deal with all of these like squares that are overlapping each other. You don't just have the number of faces of the total diagram, right? Because one square will fit like these two faces at the same time, or similarly like over here. So it is a little bit more complicated than just counting the faces, but it was a nice visualization that we were able to use to solve the problem. Okay, now we have a big rectangle and it's cut into 4 smaller rectangles as we see here. The perimeters of the 3 smaller rectangles are 16, 18, and 24. And we want to know the perimeter of the last one. Okay, let's see here. Something I might try is just giving a name to something. I don't know, we'll call this like A. And then we can probably find out what this other side length should be, right? Because this would be, well, this side plus this side has to be 8, right? Yeah, as you say over here, because the total perimeter is, 2 times the sum of these lengths. So it should be 16 over 2. So this is 8. 8 and A and 8 minus A. And then if we go over here, well, this is also A, right? So yeah, as you see on initial screen, it should be 12 minus a because it's 24 over 2. If you see like a plus 12 minus a is 12, then times 2 is 24. And then finally over here, we have 12 minus a. Ooh, can't really see that, but that's okay. And then this has to add up to 9. So I think this should be a minus 3, right? Because it has to be 12 minus 3 to get 9, and then, the a's cancel. So then this should be a minus 3 up here, and 8 minus a over here. And, oh, that's really interesting. We don't even need to know what a is, because we just get a minus 3 plus 8 minus a. They cancel out, and we just get 5 for the sum of the lengths, but then we need to multiply that by 2 to get the perimeter, which is 10. So let's see. Is B correct? Looks like it is. That's pretty cool. And I do think it is so interesting that we don't actually need to know the side lengths of that square or that rectangle in order to get the perimeter of the last one. Okay, well, this looks crazy.
All right, we have Therese, the Tyler. Oh, I love when they always repeat the letters. Always find it interesting. It's planned to make a large square, a mosaic floor with a repeating pattern, and we have these hexagonal and these triangular tiles, and they're arranged into the diagram as shown. We said approximately 3,000 hexagonal tiles are going to be used for the whole floor, and we have how many triangular tiles do we need? So yeah, this is actually definitely a really interesting tiling, but the thing I'm looking for first is essentially a sort of pattern that repeats. And if we look for that, I think actually a sort of something like this shape. Let me just outline it real quick. Oh, it's not out. All right, something like this, right? And we can sort of repeat, like in this, like this 2x2 tile, pretty much. We have another one like this, and we always have this repeating pattern. We have all of these just keep repeating, and they form this like band almost, where we keep having this repeating pattern. So for every one of these hexagons, we're gonna have to use 2 of these triangles, right? And I think that pattern will just keep continuing on. We can keep finding more and more of these shapes. And all of these should have the same sort of ratio as this initial figure that we made. So if we had 3,000 initial hexagons, we should simply need double that amount of triangles. So 3,000 just times 2, which should give us 6,000.
Wow, this is actually a really interesting solution. It's actually not at all what I was thinking. I think it's kind of hard to find this repeating pattern, but something that I was thinking you could do, well, if you had no idea how to approach this, then one thing you might try is just counting up all the triangles, counting up all the hexagons that are in this, pretty big sample size, and then that should be, about a ratio of 1 hexagon to 2 triangles. You could do that if you want. But another thing that I think you can do, so that you don't even need to find a tessellation and you don't need to count really that much, is you can just look at a single hexagon and notice that it's surrounded by, these 6 triangles here. 1, 2, 3, 4, 5, 6. But obviously we can't just, multiply the number of hexagons by 6 because some of them are shared. But for a given triangle, how many hexagons does it have? How many times are we like double counting that triangle? Well, it has 3 hexagons around it, right? So if every triangle has 3 hexagons around it, and every hexagon has 6 triangles around it, then that means that, okay, well, if we just sum up, like 6 times the number of hexagons, then we just have to divide by 3 because we're triple counting every triangle. Each triangle is represented by these 3 other hexagons. And so we can just do 6 over 3, which again gives you 2. So we can just multiply the number of hexagons by 2. So I think that's another way you could think about this problem. But either way, you get 2 times the 3,000, which is 6,000. All right, are we correct?
Yeah, for sure. That was a really nice approach. Oh, and both the answers got the same answer. Always good to see.
Nice. Okay, now we have some digits. The digits 0 to 9 can be drawn with horizontal and vertical segments. Ooh, like a digital clock. Cool. So Greg chooses 3 different digits, and in total his digits have 5 horizontal segments. Okay, so that's something, like this is a horizontal segment, I guess. And 10 vertical segments. So that's, anything that looks like this. We want to know the sum of the 3 digits. Okay, let's maybe make this a bit bigger and see what we can do with it. So I think maybe the first thing we can do is just count up how many horizontal segments and how many vertical segments we have for each of these, because otherwise, I mean, it's kind of hard to just do that by sight. So I don't know. Let's say this is like 2 horizontal and 4 vertical. Right? Each of these is a vertical. And then this is just no horizontal and 2 vertical. This is 3 and 2. This is 3 and 2 as well. This is maybe 1 and 3. This is maybe 3 and 2. Okay, halfway done. 3 and 3. And let's see, 1 and 2. 1 and 2. Then 3 and 4. And finally, 3 and 3, I believe. Okay, Anshul, where do we go from here once we have all these numbers?
I think we sort of have to sort by, because we want to have 10 vertical and 5 horizontal, and we mainly have groups of like 3, like what's it called? 3 horizontal, 2 vertical, 2 horizontal, or 1 horizontal, or 0 horizontal, really. So I think we just sort of look for these pairings that'll add up to 5. So
we need 3 numbers, right?
Yeah, 3 numbers, 3 distinct numbers.
Yeah, okay.
So if we look, I think we can have a pairing of 3 plus 2, or we can have a pairing of, well, we can't have a pairing of 3, 1, and 1 because there's only one number with 1, right? That would be, no, never mind, never mind. That would be, there's 7 and 4. So we can have a 3 plus 1 plus 1. Or we can have, 3 plus 2 plus 0, 3 plus 1 plus 1, and I'm pretty sure, or a 2 plus 2 plus 1. And I think those are the only ways to essentially get 5 horizontal. So, how do we maybe go about each of these cases?
Okay, so I think we can maybe just analyze them independently, but I think this 10 vertical condition is also pretty stringent, right? Because our numbers for the verticals are pretty small, like at most 4 and at least 2. And so to get 10, I think the only thing we can do is like 4, 4, and 2, or let's see, 3, 3, and 4. Is that right? I think those are the only ways to do it. I'm not sure if there's another way. So that is like a little bit more than the other one, but in any case, if we try 4, 4, and 2, like, okay, this is 2, 4, this is 3, 4, those are the only ones with 4, 4, and then we need something with 2, but that's already a sum of 5, because that's the 2 plus 3, that's like this case over here, and so we need a 0. And so it actually looks like 0, 1, and 8 would work. But let's just, check the other cases to make sure that there aren't other possibilities. So that's like 4, 4, and 2. What about 3, 3, and 4? Then we would need 2 3s. I see a 3 here. I see a 3. Oh, yeah, I think that's right. 3 here, a 3 here. And I don't... Oh, there's another 3 here. So 4, 6, and 9 look to be like our 3s. But we can't have these two because they would both be 3. And that would already be more than 5 horizontal. So I suppose it could be... Well, the thing is, like, all of these actually have a lot of horizontal segments. So I don't think any of these would work because they all have over 3, don't they? So I think that just doesn't work at all. And it looks like our only solution is 0, 1, and 8.
Yeah. So that would give us
go back
answer 9. Oh, some of the 3 digits. Went a little ahead of myself.
So it looks like it should be 9, which is A. And I see some agreement in the chat as well. So yeah. Hey, cool. Awesome. Let's go to the next one. Ooh, more geometry. We could do this.
Oh, all right. So we have a diagram that shows 3 semicircles inside of a rectangle, and the middle semicircle touches the other 2 semicircles, which all touch the shorter ends of the rectangle, and also all of them have basically like the sort of base touching the longest side of our rectangle, and we have these distances of 36 as the length of our base. And we have a differential of 5 and 7 between the height of our rectangle to like the peak of the 2 smaller semicircles. So I think, nice. We should sort of get a sort of diagram as well. We can label all of our radiuses, I think, or radii, just like A, B, and C. Always straightforward. All right, yeah, that's smart. Getting a bigger diagram. So we'll just call this A, B, and C, right? And the thing we know about A, B, and C is, right, if we sort of like look at that diameter, we have 2A plus 2B plus 2C equal to the entire bottom length of our rectangle. which is also just going to be just mean that a plus b plus c is just going to be equal to half of that, or just 18, right? Oh, it's a little bit off the edge. So after we get that, how do we think you should? How do you think you should go past this problem once you know that a plus b plus c is equal to 18?
Well, I think we're given some more information here. We're given that this is 5 and this is 7. So we can actually figure out b and c in terms of a, right? Because, this whole thing is a. So b plus 5 is equal to a, right? Which means b has got to be a minus 5. And similarly, c has got to be a minus 7. And so if we just, plug these into a plus b plus c equals 18, what do we get? Then it'd be, a plus a plus a, that's 3a. And we get a minus 5 and a minus 7. So we can write that as minus 12. That's equal to 18. Oh, this is nice. 3a is equal to 30. We just add 12 to both sides, divide by 3, we get 10. So it looks like a is 10. What were we actually asked for? Oh, we were asked for this side length, right? So isn't that just 10? Oh, asked for the perimeter.
Yeah.
Okay. So it's 10 plus 36, and then times 2. So let's see, that's 46 times 2, or 92? I think so. Which is answer choice B. C. We agree with this? Awesome.
All right.
Okay. Next question. Ooh. Daniel wants to complete the diagram so that each box is in the middle. Okay, each box in the middle of the next two below it, it contains a positive integer, and the product of the two below is equal to the one above. Okay, we want to know how many different values n could possibly take. So the product of these is going to be that, product of these is going to be that, the product of these is going to be that. Okay, this is interesting. I think a natural first step in this kind of problem, because we're trying to divide 720 into two factors, is maybe to write 720's prime factorization out, because I think that usually gives us some information. So let's see, 720 is 10 times 72, so 10 is 2 times 5. 72 is 8 times 9, so 2 cubed times 3 squared. So this looks to be 2 to the 4th times 3 squared times 5. Okay, so we have that. And now we need to split this into two factors. And then I think the key here is that n actually has to be a common factor of those two, right? Because n times something is that, and n times another thing is that. So it looks like we just have to find the number of possible common factors of two things that multiply to 720. So I like your idea, get in a bigger diagram. What should we do with this idea here?
Maybe we can just start off with filling in these. We're given a good suggestion. It's called the bottom row A, N, and B, and then our middle row would just be A, N, and B, N, right? And then if we multiply all these to the top, we're just gonna get A, B times N squared, right? A, B can be pretty much anything, right? We're given limitless range. Oh, exactly. And then I think someone in the chat also has the exact same idea, equal to 720. So now all we're pretty much looking for is the number of perfect squares that can be a factor of 720. So, and we already know the prime factorization is just 2 to the power 4 times 3 squared times 5. But how do we figure out how many perfect squares are factors of 720?
Well, I think we can start off by saying that n can't have any more prime factors than 2, 3, and 5, right? Because then, obviously, they wouldn't have the same prime factors on both sides. So we're going to be something like 2 to some power, 3 to some power, 5 to some power, but actually, I can't have any 5s either, because if I have a 5, then this would be 5 squared times something, but on the right-hand side, I only have a 5. So we can just forget about that, and we're just looking at 2 to the 4th times 3 squared. And if n squared is, a divisor of this, if it looks like, say, 2 to the a, oh, we already used a, 2 to the alpha, and then 3 to the beta, then if we square it, if that's what n is, then if we square it, we get n squared is 2 to the 2 alpha, 3 to the 2 beta. And the thing is, this has to be, 2 alpha has to be less than 4, or less than or equal to 4, and 2 beta has got to be less than or equal to 2, right? Because we're not allowed to have more factors of 2 than in the number. Otherwise, it wouldn't be a divisor. So that means that alpha has to be at most 2, and beta has to be at most 1. And so the only options are actually alpha, just looking like 0, 1, or 2, and then beta just looking like 0 or 1. And so there's actually not that many options here. There's 3 options for alpha, 2 options for beta. Looks like the number of ways in total will be 3 times 2, and as you see on Anshal's screen, that would be 6. So is that the correct answer? Well, is that an answer choice? Yeah, it looks like it is. It's option D, and it is correct. Awesome.
All right, we're on a roll, and all right, we're given this really sort of unique diagram. Almost looks like a crown, and we have these 3 angles: alpha, beta, and gamma. I think that's the letter. So now we need to find out the sum of the angle, and these are always really interesting problems because almost always you have to rely on pretty much sort of rearranging that. So I think a good idea is to split B down the middle and sort of solve for almost like well, because the thing is, what I'm seeing here is if we take a look at this shape right here, that's going to be half of beta, right? But what also could happen is we can sort of move it to this side, right? Because we're summing them all up, right? It doesn't really matter how we arrange that. We sort of flip it over. This is just going to be, this angle is going to be beta over 2, right? And we can do that on the exact other side as well. And this is going to be beta over 2. So now that we have these almost two of these bigger angles, how do we solve for the total angles? A total is pretty much sum of all these angles, Eli. How do you think?
Well, this is an interesting approach. It's actually not what I was thinking, but I think we can still run with it. Because over here we have, beta over 2 and plus alpha makes this kind of shape here. This is kind of hard to see, but you can see this. And then over here you can do something similar with this shape that you get here. And now I think the key, well, something you can notice here is that this is 3 down and 3 across. And so this should actually be, I think this is where you were going. This is a 45-degree angle, right? Because this is 3 and 3, and this is a right angle. So it's an isosceles right triangle. And so this whole thing would be 45. Now I see what was going on. So if this is 45 and this is 45, then it looks like the sum of everything, which was just rearranged, would be 90. And so, yeah, that's actually a really, really cool approach. It's not what I was thinking. I want to say quickly what I had in mind for this problem, although I think that was a really cool idea, is that actually we don't even need to split anything up. We can just move them around. So if we say move, I think it should be, yeah, let's move the beta over here. I have more space on the right. Okay, we'll move beta over to the right. So this is the same length as this, right? So we can shift this entire angle beta and then just rotate it a little bit. And if we continue our grid lines going over here, I'll start to write on my face, that's okay. Then we'll have something like this. And this is going to move over here, right? Because this, yes, this is this length, and this is 2 across. So actually, this would be over here. This is beta now. Okay, so this is the new beta. And then finally, this alpha over here is going to attach, because this is the same length as this length here. This is going to attach over here, and it's going to move over 2 as well. So it's going to be all the way over here. And so then this is going to be alpha. And so we have this whole thing like this. And this is alpha plus beta plus gamma all in one angle. And we see that actually this is 3 across here, but it's 3 times root 2 because each of these is a diagonal of 1 and 1. And then all across here is actually a length 6. So we have 6, 3 root 2, and 3 root 2. So in all, I believe this should be another isosceles right triangle, but now this is the right angle. And so we see the full 90 degrees there. So actually, I think your approach, Anshul, was even better because it didn't require, drawing more stuff.
Okay.
But I think this is another way. Then you get the entire angle all in one. So yeah, 90 degrees. Are we correct?
Oh, yeah.
We are. Awesome.
All right.
And I think this might actually be the last question we're doing. So let's savor it, I guess. Alex drives from point A to point B, then immediately returns to A. Bob drives from point B to point A, then immediately returns to B. Okay, so it's a little interesting because they're called Alex and Bob, which is A and B, but the points are A and B. Okay, they travel on the same road. They start at the same time, and each travels at a constant speed. We know that Alex's speed is 3 times Bob's speed, and they pass each other for the first time 15 minutes after the start. Okay, I think I got it. And we want to know how long after the start they will pass each other for the second time. And I don't know if Anshul was just giving away the answer for a moment, but you didn't see anything. So, Anshul, where would we start here?
Maybe we just define our sort of points A and B, and sort of maybe define our points Alex and Bob, and see how far they would travel in maybe in a set amount of time, or maybe like we graph their sort of intersection point almost relative to A and B. So we're given A and B here, and we know that Alex starts at A and is going towards B, and then going back to A, and then Bob is traveling to A and traveling back to B. And Alex is 3 times quicker, so pretty much if we sort of look at our diagram, this distance in the first meeting has to be 3 times the distance Bob travels, and if that's true, they're going to meet at roughly this 3/4 marks between the distance from A to B. But Eli, how do we sort of go past that and look for their second intersection?
Yeah, so I think here it might be helpful once we know that this is 3 and this is 1. I mean, however you want to do it, it doesn't really matter what units we're using. So we might as well just say that this is 3 miles and this is 1 mile. That now we have to say that A is going to get to B and turn around. So, well, once A gets to B, oh, well, this is so confusing. Once Alice gets to B, where is Bob going to be? Well, Alice, runs at I guess this is what, 3 units per our time. So, 3 times faster than Bob. So once Alice gets over here, which was a total of 1 unit, then Bob probably moved 1/3 of a unit over here, right? So this would be Bob's new location is 1/3 over, and now Alice is going to be at point B. And so now at this point they're actually moving in the same direction, but Alice is moving quicker, so they're going to converge, eventually, some point, over here. So how can we figure out exactly where and when they're going to converge at that point?
Well, I think the numbers actually really line up nicely for us, because if we think about it, if we sort of look at our initial intersection point and Bob moves exactly 1 unit further, then Alice will hit that 1 unit further and also hit 2 more backward, adding up to 3. And the numbers just really line up just really nice, because once there's 1 and then there's 2 more backward, and then Alice and then Bob. Okay, wait, the names are mixing me up. But we'll move at a distance of 2 also in that same amount of time. So the numbers, I don't know, they just really line up nicely. I can't lie.
That is true. Like, we don't actually need to do any equations if we just notice that it needs to go 2/3 more to get at the 2 mark, and this needs to go 2 more to get at the 2 mark. So that would be 2 either way, and that's when they would meet. So that's kind of awesome. And so once we know that, then we just have to find how long it takes. But let's see. I mean, A traveled a total distance of 4 and then 2, so it traveled 6. And we know that A traveled 3 miles, I guess we're saying. Choose a different color. 3 miles in a time of 15 minutes. So if A is now traveling 6 miles, then it's going to be 6 miles in 30 minutes, right? We just multiply the values by 2. And so it looks like we would get option C. And it's kind of amazing that it all just works out. It looks like Jen agrees with me as well. All right. We are correct. It is 30 minutes. Okay.
All right.
I think we're actually out of questions. So, yeah, I don't know if we do anything else now, but thanks everyone for coming otherwise.
Thank you guys for coming.
Hope you enjoyed these questions as much as we did.
For sure.
And